Hello students, I'm Joaquim Brugués and I will be offering you a lesson on Morse theory. So this is not something strictly contained in the contents of the course, but Eva and I thought that it would be nice for you to have some insight on this theory. So I will tell you the basics without going deep into the details. If you want more information on anything that I told you about in this lesson, I will point you out to some bibliography that you can check. So you can check Milnor's book, Morse Theory. This is an excellent reference. This was the first book where everything about Morse theory was properly compiled, and this is an excellent resource. But where everything that you don't find here, you will be able to find it in Morse Theorem for Homology by Odin and Damian. This is also an excellent reference, and it is more modern, so perhaps it's easier to read, but most of the theory it's overlapped between these two books. Also, I am including here lectures on algebraic topology by Dolt, because in this lesson, and of course in the books, there will be references to something that you may not know, which is cellular homology, and this is not the place to define it properly, but here you will be able to find the definition and properties and everything you need. So, going to Morse theory proper, as said in the notes, the goal of Morse theory is to reconstruct the topology of a manifold using a Morse function. And this is a very good way to summarize this. The idea is that to understand topologically, of course, a manifold, you use a radiography of it given by the critical points of a function. We will see precisely what this is about, but of course the main tool that we're using here are Morse functions, which you already know, and I will comment here on the most important properties that you already know about Morse functions. So first of all, the definition is that the critical points of a Morse function are non-degenerate. This has the consequence that they must be isolated. You cannot have a sequence of critical points converging to anything. You have the Morse lemma, which you have proved, I think, in class. And this is a very important construction that we have on Morse functions. So locally, around your critical point P, you have this local form of the function. And what is remarkable about this is that the number of variables which carry a negative sign here, and it is something that's invariant on the chart, on the Morse chart that you choose. So if you shuffle your variables, if you change your chart in any way, that's still a Morse chart, so this has this form. The number of negative directions, this number k, is invariant. It won't change. And of course, the number of positive directions won't change as well. I think that in a video by Eva, you have seen the proof that Morse functions are not rare, in the sense that you can always find a Morse function for a given compact manifold, and even that they do not only exist, but they are dense in the set of smooth functions. So you can always find a Morse function which is arbitrarily close to a given smooth function. But there are more properties of Morse functions which are important, and the crucial one, which we are focusing on in this lesson, are the Morse inequalities. So Morse inequalities do exactly what we said at the beginning. If you have the number of critical points of a Morse function, and you select them by the index, which I think that you already know the definition of index, but if not, this is going to be recalled in short. These numbers are related to these topological invariants, which are the Betti numbers of your manifold X. So you have these inequalities. This is a non-intuitive thing at all, because this is a function. This belongs to the analytical realm in a way. Its critical points could be any number a priori, but what this is saying is that no, you have a lower bound, and this sometimes is presented in this weaker way. So we say that the number of critical points of the function is bounded by the sum of the Betti numbers, but of course this is a stronger assessment here. So to begin with, I'm not going to jump directly to the proof of these inequalities, because this is what the motivation to develop the whole Morse theory. First, I'm going to present a similar result, which is the Reeb theorem. So the idea of the Reeb theorem is that if you have a compact unconnected smooth manifold of a given dimension, and you have a function in this manifold that has exactly two critical points, then your original manifold is homeomorphic to a sphere. The topology of the manifold is a sphere. So the reason why this is a striking result is that if you think about it, you have the Weierstrass theorem that tell you that a manifold must have at least two critical points, because we are working with compact manifolds, and compact manifolds need to have at least a minimum and a maximum, and in a smooth context they must be critical points. So this theorem in a way is giving you more information about that. It's saying if your manifold is not a sphere, if you know that this is not a sphere, then you need to have at least three critical points. So we can see that we are getting lower bounds on the number of critical points already without working properly with Morse functions. So I won't explain the proof of Reeb's theorem, but you can find it in the notes of the course. I will just give you an idea of how this is proven. So the idea is that you need to use another result which is more general and has no other applications, which is this proposition. If you have a function on a smooth manifold and you have 2 points in the image of the function, you take them such that the anti-image of the closed interval is compact and does not contain critical points. This is the crucial thing here. Then you have a retraction result, which is the following. This set XA and this set XB are defined in the notes, but the idea is that the set XA are the points of the manifold whose image by F is lower or equal than A, and XB the same, the points on X whose image by F is lower or equal than B. So you have like slice cuts and subsets inside of your manifold. These are smooth manifolds, topological manifolds and everything. So also you can think that if A is lower than B, which it's our choice here, then XA is contained in XB. This is easy to see. Then XA, the small set, is a deformation retract of XB, and moreover they are homeomorphic. So before jumping to the proof, I will show you this figure. The idea is here, okay, this is my choice of manifold. This is this kind of cylinder which splits in two, and we choose these heights here. Here we have the function f. We choose xa in this height, and we choose b in this height. So xa is this part of the manifold which is below a, and xb correspondingly is this subset. And here we can see the idea of this proposition. The idea is that if we take xa and we expand these cylinders in any way, the topology of the manifold does not change at all. And conversely, if we think about xb and we retract these cylinders that are dotted here towards these endings, the topology is the same. The homological class does not change at all. So we have a homeomorphism. At least that's the idea. So to prove this theorem, the main idea is to introduce a metric in x, and we take the gradient of our function f. And we need to restrict ourselves to this set, because what we want to do is to normalize the gradient. So we have to use step functions also to define a vector field globally, which I denote here by y. So we normalize the gradient and we take a step function to have a vector field globally, and we take the flow of that vector field, which is an extension of the gradient of f, which is normalized, so all the details can be found in the notes. And taking that flow, you can construct the movement that goes from this set xa to this set xb. So you construct this expansion or retraction as you want to see it. And this is the idea of the proof. So I will leave you to check the details on the notes of the course. So the idea to prove the original theorem that we were interested in, which is Reeb's theorem, is to use this assertion, and this is also explained in the notes, but the idea is that by Morse lemma, since you can find, well, you don't need to use Morse lemma actually, but you can find small disks around both critical points, and then you can argue that from one of the disks using this proposition here. So this disk can be expanded until it touches the other one, and then you need just to prove that they fit nicely, and then you have a sphere of the dimension of the manifold as stated here in the proposition. So this is the idea of Reeb's theorem, and of Reeb's theorem, sorry. So the idea is that the tools that we have developed here can also be used in more general senses. So a question that was tackled some 60 years ago was what happens if our set contains a critical point, like what happens if it contains this critical point here. Of course the topology between this cylinder here and this split cylinder here is changing, but can we control in any way how this topology changes? So I won't go in depth in this lesson about these results and how they were tackled, but you can find them in the references. So we need to define the index of non-degenerate critical points, and there are several versions of it. I think that you already saw a definition, but to recall it, the definition of the index of a critical point P can be seen algebraically. This is the most standard way. So you take the Hessian of your function, this is the second derivatives matrix in your critical point, and the index of P are the number of directions in which each P of f, the Hessian, is negatively defined, or equivalently you can just count the negative eigenvalues. However, there are alternative ways to see it. For instance, if you just use Morse lemma, this invariant k that I commented on before is precisely the index of your critical point. So this is a different way to see it. But the most interesting one is the dynamical interpretation. So if you consider the negative gradient, and the reason why this is negative will be apparent when we look at examples, but this is mostly for historical reasons, but just hold on with me. If we look at the dynamics of this vector field, at least close to our critical point, as this is not degenerate, we see that we only can have an unstable and a stable manifolds. So the easiest thing is to just take the index as the dimension of the unstable manifold. If you, for instance, if you take the gradient locally of this expression, you will see that this is exactly the same. The negative directions are the directions in which the minus gradient expands. The flow of your minus gradient expands. So this is the dimension of your unstable manifold. But this is what's interesting. The idea of Morse theory, in a way, is to, for each critical point, you take its unstable manifold. This forms a disk inside of your manifold, and what you want to see is how this relates with the other unstable manifolds, and so on and so forth. So from here we have the ingredients to define the groups of our complex, because we will define a homology here. This the result that we want to prove, Morse inequalities, have to do with homology. So the way to prove this theorem will be to construct a homology that takes into account the critical points, and once we construct it, we will relate it to the simplicial homology, the one that defines the Betti numbers. So the way to define the groups of our complex will be to use the critical points of a given index of a function. And before we go further, of course you can choose any ring to define your homology. Usually one uses Z, or the real numbers. Z is the simplest usually, but you can even go simpler to Z2, and here I'm going to use Z2 because if you use Z, then you have additional complications when you define the complex itself, because you need to take into account orientations of the unstable manifolds. So to not take into account all that complications, I'm going to take just Z2, which is good enough to prove the inequalities. So the kth Morse complex group is the free group which is generated by the critical points of index k. So you take all the critical points of a given index, and you can take any free symbolic, if you will, linear combinations between them with coefficients in Z2. This is what this notation means. So to define a homology, we need the groups, of course, but we also need a boundary map. And this is the dense part of the theory. So in order to define the boundary map, we will need to relate a given critical point with critical points of less index. So we will do it using the stable and stable manifolds, and of course using the minus gradient. So let us make an assumption. Assume that for two critical points, A and B, the unstable manifold of A, so the directions in which the flow descends from A, and the stable manifold of B, so the ascending directions in a way. So you want to impose transversality in that intersection. If you have that, the intersection is a manifold, and the dimension of the manifold can be easily computed because you have the equivalent of the Grassmann, I think it was called the Grassmann formula for dimensions of vector spaces, you have the analogous here. So if you have the intersection, its dimension is the sum of dimensions minus the dimension of the total. So the dimension of the unstable manifold is the index of F, and if we recall before, I said to you that a critical point can only have stable and unstable manifolds. It cannot have anything else in its dynamics because it's non-degenerate, so we are imposing a rigid condition on the dynamics. Imposing that the dimension of the stable manifold must be n minus the index. So if we apply the formula, we get that the dimension of this intersection is the difference of the indices. So this is telling us in particular that the index of A must be greater or equal than the index of B for this to make any sense. So we will be using this, and therefore we want our vector field to satisfy these conditions. So we can impose this as in a way a condition in the same way as we impose that F is a Morse function. We can impose its gradient to satisfy this Smale condition, so that all the stable and unstable manifolds intersect transversally. And if we ask ourselves if this condition is too restrictive, so we cannot construct this complex at all, it is not. I'm not going to prove it here, but in the references you can see it extensively. There are two ways of doing this. The most intuitive way is that you can deform the Riemannian metric that you use to define the gradient, and doing a small deformation, this condition will be satisfied always in a generic sense. Another way to do this is not take into account the metric and construct something called a pseudo gradient. This is the approach, at least in Damian and Mikhail's book, and Odin and Damian's book. And this deformation can be, so this pseudo gradient, is a vector field introduced in a way so that around critical points it has the exact same dynamics as the minus gradient, and if you are far away from any critical point, then you have a condition that allows it to behave similarly to the gradient. And of course we ask that the fixed points of that vector field are exactly the same as the minus gradient. So there are two ways to do this. We are going to go with the deformation of the Riemannian metric. Okay, having this, what we can do is study this intersection that I just commented here. So this is a manifold, we know its dimension precisely, and we know something else. We know that we have a natural action by R, and this action happens because the intersection does not contain the critical points. This is important. It does not contain P and Q. And here, inside of this intersection, we do not have fixed points by our vector field. So we can always move things around using the flow. So when this flow tends to plus infinity or minus infinity, you will reach P or Q. Oh, I'm sorry for using P here, it can lead to confusion. This P is a random point inside of this intersection. And the idea is that this action is free because of what I just told. This flow moves everything. If t is different from 0, t times p will always be different from p. And therefore, we can quotient this, and this quotient will be a manifold. So I think you have seen this with Eva in Lie group theory. This is a construction that is used in a lot of fields, not just in Morse theory. You will see constructions analogous to this if you study other fields, for instance, floor theory or a lot of symplectic homologies. The definition is this: is the trajectories that go from P to Q, but you don't want the points of the trajectory. You want to identify the whole trajectory as a single point. And it's worth mentioning that this Modulli space has -1 dimension with respect to the previous one, so the dimension is the difference of indices -1. And I won't prove it here. This is the complicated point. Modulli spaces, well, they are not actually compact, I'm lying to you here, but they are pre-compact, so you can always compactify them in a nice way. We will see examples of Modulli spaces later on in the examples. But the important thing is that Modulli spaces are used to define the boundary map that I was telling you before that we need. So the idea is the following. If we have two critical points A and B which have consecutive indices, then the Modulli space has dimension 0, and in this case this is compact. This does not have any weird behavior. So this is a collection of a finite collection of points. So we can count those points, and this is legal. This is what you will do if you are in Z2 and then you need to take modulo 2. So you are not just counting the points, you are counting the points and then quotienting it by 2. So you are checking the parity of the number of trajectories. Or if you are in Z, then you need to count the points, but you also need to add a plus or a minus according to orientations. As I told you before, you can check that in the book by Damian and Odin. So the boundary map is just using these numbers here. You take a critical point, you take all the points of index of the following index, the -1 index with respect to this point, and you take this formal sum and counting these numbers. So this is a valid expression because this is a way to define the boundary map on the generators, as this is usually done in the boundary maps of complex. So it can be proven, this is also a complicated thing, it can be proven that consecutive boundary maps equal to 0. So this is a proper complex. This is the crucial point. After proving this, we know that these groups form a chain of groups, and therefore you have a complex chain of groups. So having this, you can compute the homology of that complex chain, which I will recall to you that is the kernel of each map quotiented by the image of the one that goes before. We can see it is important to note, that everything that we have defined here depends in all of our choices. So it depends on the manifold, of course, it depends on the Morse function that we have chosen to define this complex, and it depends on the Riemannian metric that we have used to define the gradient. And this is important because this is not a topological invariant still. This is an invariant that depends on these three things. But the nice thing is that it can be proven that you have these right invariants that we want. So the first theorem tells us that Morse homology does not depend on the choice of Morse function or on the Riemannian metric J. So if you choose different Morse functions or different vector fields associated to them, you will always find the same homology as long as your choices allow you to define this homology. The complex chain can be different, we will see an example of that, but the homology is an invariant, and as it only depends on the manifold, it can be thought as a topological invariant. And this still does not prove Morse inequalities, but you still need this last theorem that says that Morse homology is isomorphic to the simplicial homology. Again, not the complex chain, but the homology is the one that is equivalent to your simplicial homology. Here I'm stating that the simplicial homology, of course, needs to be defined on Z2 as well. So this is the proof of the inequalities, if you think about it. Because here, beta sub k is the topological information, is the dimension of the kth simplicial homology group. And ck is the number of critical points of dimension of in the index k. So it's the dimension of the kth complex chain group, so of Cm or sub k, the one that I'm defining, for instance, here. And the nice thing is that the homology group of index k will have always less rank than this, less or equal. So the inequalities are satisfied because of this theorem. So this is the whole theory. But I think as I have just skipped through the whole of Morse theory, probably not everything is quite clear. So I have compiled a couple of very elemental examples to help you visualize some of the things that I have explained here. So the first example is just the sphere, as we can see in this figure. You can imagine it embedded inside of R3, and our Morse function will be the height function. A natural question is if the height function is a Morse function. Trust me, it is. You can check it very easily. And the critical points are only the north and the south poles. So this is a very elemental example, because the Morse group of index 0, of rank 0, sorry, will be generated by the south pole. So it's just equivalent to Z2. We don't have a Morse group of index 1 because there's no critical point of index 1, and the second rank group of the Morse complex will be the one generated by the north pole, so equivalent to Z2. In this case, we could define the boundary maps, but everything is 0 because you don't have any two consecutive Morse groups that are not trivial. What is worth thinking about is what is the Modulli space of N and S as defined here. So we can think about it. The unstable manifold of N is just everything, all the points of the sphere except of the south pole, because the unstable manifold are the points who such that if we take the flow towards minus infinity, they reach N. And in the same way, the stable manifold of S is all the sphere except for the north pole. So these are these two disks, and the intersection of them is the whole sphere except of the poles. And the action by R is the flow in this vertical direction. So if you take the equation, you can think that the Modulli space in this particular case is this circle, for instance, the equator. In this case, it's not relevant because we don't need these Modulli spaces to define our boundary maps, but this is the idea. And notice that the dimension of the Modulli space here is 1 because the difference between the indices is 2. Now I'm going to show you the same example, but a little bit different. So we'll take a look at this figure here. This is the sphere, the same as before, but we're taking a different Morse function here, such that it has this way of embedding inside of R3. So this example will be having this figure embedded inside of R3 and taking the height function as before. I'm going to leave you to compute this. So if you want to try and crack this one yourselves, just pause the video, take a pen and a notebook and try to compute it. And once you have gotten it, or you think that you got it, or you think that this has no solution, then go back to the video. So the idea is that the critical points here, this is just a hint, so you can listen to this still and try again. The critical points here are this local maximum, this other local maximum, this saddle point, and here the global minimum. You have a total of 4 critical points, these 2 of index 2, this of index 1, and this of index 0. So you can think about the trajectories that go from one critical point to another and try to count the modular spaces in this way. So if you want to try again, try now. So the solution of this exercise is here, which is a little bit long. Alright, I've called the critical points of index 2a, a1 and a2. The critical point of index 1 is b, and the critical point of index 0 is c. So the first thing is to compute the Morse groups only, and they are these ones, these 3 expressions. So the Morse group of rank 2 is generated by 2 critical points, so is equivalent to z2 times z2. The Morse group of index 1, of rank 1, sorry, is equivalent to z2 only. And in the case of index 0, you have this. And now it's the moment to think about the Modulli spaces. So if we look at A1 and B, they are critical points of consecutive indices. Perfect. And if you compute the unstable manifold of A1, for instance, is the whole half of this figure, without including this circle here, is this disk that takes up all this half of the figure. And the stable manifold of B is the whole line that connects A1 towards A2. All these trajectories here. So if you compute the intersection between A1 and B, you will find that it is this line without including the critical points. And if you take the quotient, it's just 1 point. It's just of a single point. So you can say that the boundary map of A1 is just B, or 1 times B. The same reasoning holds for A2. And now comes the interesting thing. If you compute the Modulli space between B and C, you'll find that you have 2 trajectories, the one here and the one here. So the boundary map of B is 2 times C. But as we are working in Z2, this is just 0. So this partial delta 1, to call it some way, is just 0. So this is easy. And now to compute the homology groups, we need to compute the kernel of each of the maps and the image. So this can be easily seen as this. Here I'm using the minus sign to emphasize that you need to subtract them, but of course in Z2 it's the same to subtract or to add these 2 critical points. And now, having all this information, we can compute the homology. So if we take the whole chain of groups, I put this in a way to give an intuition. Okay, the second homology group is just the kernel of delta 2 because we don't have anything on the left. And the kernel of delta 2, we saw it before, it's the one generated by this expression. And this has dimension 1. So the first homology group is Z2 only. The first homology group is the kernel of delta 1 quotiented by the image of delta 2. If we take this into account, we will see that if you allow me to go back 1 second, delta 1 is 0, so the kernel is the whole first Morse group, and this is the one generated by B. And the image of delta 2 is exactly the same. So it's not striking that the quotient between these two groups is exactly the trivial group. And finally, the last homology group, perhaps it's not well defined in general, but you can just think that this map is the zero map, so the kernel of this last boundary map is the whole group. So this is what we call the co-kernel of this map. This is the whole group quotiented by the image of partial 1. And if you compute that, you will see that this whole group, of course, is the one generated by C. And delta 1 is the zero map, so its image is trivial, and therefore you get the same homology group. So the topology, the end result, the homology is exactly the same as in the other example, as in here, but of course the reasoning is different. The groups of the chain complex are different. So this example is here to stress the fact that the complex chain can vary, but the homology is invariant. And of course you can check here that the Morse inequalities are satisfied. Of course, the first homology, the first Betti number of the sphere is 1, and here we have 2 critical points. The second Betti number, the first Betti number is 0, so the inequality holds, and here the 0th Betti number is 1, so you have an equality in this particular case. Alright, I'm going to present you another example, but I'm not going to compute it, I'm just going to give you an idea. So you can try with the torus, which is usually in a standard example to introduce Morse theory. The thing is that if you take a torus like this, and you try to compute the Morse homology here, you will find a problem. This does not satisfy the Smale condition, as it is. And you can try and check why. I'm going to tell you why. I'm going to tell you why in a second. The reason is that the unstable manifold of B1 and the stable manifold of B2 do not intersect transversally, actually, because it should be of the intersection should have dimension 0, but the intersection has dimension 1 in this case. So here we cannot construct Morse homology directly. We need to do a small deformation, and I'm proposing you this one. Instead of choosing a different Riemannian metric or choosing an equivalent vector field, just change a little bit your function. If you tilt the torus in this small way, you will find this dynamic. Perhaps this drawing is a little bit confusing, but the idea is that this point is behind of the picture, and the trajectories are clearly drawn here. So here you can try to compute this example, and you will find that this is very easy. And you can try with other examples, for instance with complex projective spaces or real projective spaces. You can look for an appropriate Morse function for a projective space and try to compute the homology and check that it actually coincides with the simplicial homology. So I will leave you with that. And well, last and not least, I will say you farewell and wish that you take care in these difficult times. Alright, bye.